Hi, my name is Austin Marangoni, and today I will be talking about 3D transistors. So first, let's start off by talking about the history of transistors. So what is a transistor? Well, a transistor is a semiconductor device that is used to switch or amplify electrical signals and power. It was first patented by Julius Edgar Lilienfeld in 1925. Though Lilienfeld was the first person to patent this invention, he did not write any research papers about it, nor did he actually make the device, because semiconductors were not readily available until World War II, and because of this, his invention fell by the wayside. So during World War II, Bell Labs was tasked on creating pure semiconductors for the war effort. They were designing germanium crystal mixer diodes, which take in two signal frequencies and outputs a signal that is the product of the two input frequencies. They were used in radar equipment to compare sent and received signals. So after the war, William Bradford Shockley Jr., a Bell Labs physicist, was free to continue his work on semiconductors. Shockley decided he wanted to build a semiconductor device similar to a triode. So you might be asking, what is a triode? Well, a triode is a vacuum tube device that is used to amplify an electronic signal. Triodes get their name from its three electrodes: a heated filament, which is the cathode, a metal mesh control grid, and a plate anode, all inside an airless glass tube. A triode works by heating the cathode filament, causing it to emit electrons as a result of the thermionic effect. These electrons flow through the vacuum tube unencumbered by gas molecules through the control grid and the plate anode, where the electrons are collected. This creates a potential difference, or voltage, across the anode and the cathode. The electricity through this device can be controlled by applying a bias to the control grid. A strong negative bias on the control grid repels the electrons, preventing them from reaching the plate anode. So Shockley acquired funding for research in lab space to experiment, and he started his work. Shockley's team discovered that if they applied a voltage to a crystal in a certain direction, no current would flow. But if they injected electrons into the crystal, electrons would begin to flow. In 1947, after a few years of experimentation, Shockley's team at Bell Labs successfully built the world's first functioning contact transistor, which you can see there in the bottom right. So how did it work? Well, the transistor consisted of a metal base, atop of which was a p-type germanium crystal, on top of an n-type germanium crystal. Resting on top of these germanium crystals was a plastic triangle with gold foil electrodes along the two sides. These gold foil electrodes form the emitter and collector. At the vertex of these two gold electrodes was a very tiny slit separating the electrodes. So the point contact transistor was commercialized and sold for a short while until it was superseded by the BJT, which is a new transistor technology. And in 1965, Shockley and his team were awarded the Nobel Prize in Physics for their researches on semiconductors and their discovery of the transistor effect. So now transistors are starting to enter the consumer marketplace. And so William Shockley Jr. Continued his work on the transistor, and in 1948 invented another revolutionary device, the bipolar junction transistor. This new transistor operated on a completely different principle to his original point contact transistor. BJTs could be made much smaller and much more cheaply than the old transistors, allowing them to be used in consumer goods. One of the first transistor-based products to enter the market was the transistor radio. For the first time, consumers were able to listen to radio broadcasts wherever they were, not only at home. Before transistors, radios were based on vacuum tubes, which were large, therefore not very portable, and the heating elements made them power hungry, discounting the use of batteries. And here's what the radio looked like inside. The transistor radio did not have many of the problems that the older vacuum tube radios had, so therefore it was a hit. The transistor radio actually became the most popular electronic device in history, selling billions of units in just 10 years. And so in 1953, the first experimental transistor computer was built by the University of Manchester. The machine consisted of 92 point contact transistors, and it quickly grew. By 1955, the computer had been upgraded to a total of 200 point transistors, and it consumed about 150 watts of power. And since point contact transistors were not very reliable, the machine could only run for about an hour and a half. And so by the 1970s, the number of transistors in computer processors was up to 2,000 transistors. And then by the 90s, there were over 1 million transistors in computers. This trend of ever-increasing number of transistors in microprocessors was noted by Gordon Moore, an American electrical engineer who later went on to found Intel. And here is a chart showing the course of this trend. The trend was named after Moore, being called Moore's Law. It stated that the number of transistors in a microprocessor doubles roughly every 2 years. And so now that we have a background, we can start talking about 3D transistors. So in order to keep pace with Moore's Law and shrinking devices, researchers had to come up with a new innovation, the three-dimensional transistor. As transistors got smaller and smaller, chip manufacturers found themselves experiencing short channel effects. A short channel effect is when a metal oxide semiconductor field effect transistor, or MOSFET, when its channel length is near the same length as the depletion layer of the source and drain. These short channel effects can cause electron drift in the channel, and it can change the threshold voltage of the MOSFET. So in order to gain more control over the gate, researchers have invented MUFETs, or multiple gate field effect transistors. These MUFETs are a type of MOSFET that has more than one gate in a single device. Typically these multiple gates are connected, so they act as one single gate. And MUFETs that have independent gate electrodes are called MIGFETs, or multiple independent gate field effect transistors. While there's dozens of different types of multi-gate transistors, the most common are planar double-gate transistors, flex FETs, FinFETs, and gate-all-around FETs. So the FinFET is a new kind of MUFET that was developed by UC Berkeley researchers Chen-Ming Hu, Su J-King Liu, and Jeffrey Bokor in 1999. This FinFET was done by creating a fin of silicon that protrudes upwards into the gate. These transistors are called FinFETs because of its fin-like protrusion. As you can see, there are many different topographies of the FinFET, each with its own advantages and disadvantages. So as you can see on this graph, so MOSFETs do not experience short channel effects if the length of the gate is 4 to 6 times larger than the natural length, lambda n, where n is the number of gates, which would be 3 for the FinFETs, as they are tri-gate devices. And you can use this formula to calculate lambda n. So as you can see on this graph, the ratio of channel length L to the natural length lambda n increases, so do the effects of the drain-induced barrier lowering, or DIBL. Drain-induced barrier lowering is a short channel effect which leads to the lowering of the threshold voltage at high drain voltages. Since the source and drain have increased contact with the gate, the FinFET has improved control over the channel region, minimizing short channel effects. And so FinFETs, although they may allow us to make smaller transistors, they come with their own set of challenges. Because of their three-dimensional characteristics, silicon chip fabricators can no longer use their previous lithography techniques to produce their FinFET-based chips. Chip fabrication facilities need to be retooled to produce FinFET devices, and it's a very, very costly endeavor. So manufacturers have been using technology CAD or TCAD software to model their semiconductors in multiple different ways, so that they know that they'll work the way they want them to before they remake their facilities. And so FinFETs are beginning to make their entrance into the consumer market. Intel, almost certainly being the industry leader in this field, has already introduced a 22 nanometer and a 14 nanometer process for producing FinFET-based microprocessors. Intel did experience some hiccups switching from their two-dimensional process to a three-dimensional one. Intel was known for their tick-tock release schedule, introducing a new architecture in one generation, and then they'd use the same architecture in the next generation, but they would shrink the process to a smaller scale. So Intel had to part with this tradition with the introduction of their Haswell architecture, which was the first FinFET-based architecture of their lines. So, in conclusion, the three-dimensional transistor technology may be the key to continuing with Moore's Law for now. As consumers seek smaller and sleeker and more powerful devices, companies like Intel will need to keep innovating to keep their customers satisfied. Although there have been some kinks in the introduction of three-dimensional transistors to the marketplace, they are now starting to be seen in more and more devices. So that's the end of my presentation. I hope you enjoyed it. I hope you learned something. Thank you.